Alright, folks, we're going to look at Cevians and then Ceva's theorem. So to kind of understand what a Cevian is, I'm not sure if I'm pronouncing it correctly. Cevian. So so I do apologize if I'm pronouncing it wrong. So, a Cevian is a line segment in a triangle drawn from a vertex to the opposite side. So you can kind of visually kind of just see, like, if I just draw a triangle here. And then basically a Cevian can be any line starting from a vertex, and I can draw it anywhere to the opposite side. So it can be from down here, or it can be to up there. It doesn't really matter what it is. The general definition is just cut from the vertex to the opposite side in any way. So we actually covered one of them in the previous video, assuming you're watching them in order. One of them is the angle bisector, where effectively we cut the angle in half, we bisect the angle, and then we just draw it to the other side. Doesn't necessarily matter where on the other side the line touches. It's still a Cevian. There are two others we'll look at in later videos. One is the median, drawn from a vertex to the midpoint of the opposite side. So it's drawn from the vertex to the midpoint, but the important part is the midpoint. And then the altitude, drawn from a vertex perpendicular to the opposite side. So that's already like a perpendicular bisector almost, but we'll clarify that in later. So now the thing about Cevians is that we've got a nice little theorem called Ceva's theorem, and the idea is that it is a relationship between the ratios of the sides of the triangles in a slightly different way. So we've got a triangle ABC here, and we've drawn our Cevians in some particular way, and now we see that if the three lines are concurrent, so they meet somewhere, not necessarily in any particular order, then we have a set of ratios. So the important part about these ratios is that, pardon me, I was just wiping something off my iPad. So if you look at AZ to ZB, you will see that it's from A to Z, and then Z to B. So you can kind of see is that where Z cuts AB, then you've got the ratio of the two lengths. And then similarly for BX and XC, what's happening here is you got BX, and then XC, and then for the last one, you've got CY and YA, CY and YA. And so effectively it's saying, okay, if we multiply all these ratios together, they actually end up to be reasonably equal. So the proof of this is sorry, I really shouldn't, should at least leave that up. So I should leave that up so that if you read the notes, you understand what's going on. All right. Proof. Okay, we want the proof of this. So, just trying to think about how to go about doing this. Okay. So, all right. What I'll do is that I will copy this one over because I'm gonna need that diagram, and then gonna copy, and then I'm gonna paste it over. Paste. Oh, sorry. Okay, I'm an idiot. Alright, so I will color this in later because I just want to copy the image for now. Alright. It's been a long day today and I'm still recording videos. Alright, let's do this properly. So paste image, there we go. Gonna expand it because I definitely need to indicate a few things. Alright, sorry about that. So that's gonna be A on the top. Now, the first part of what we're going to start with is by identifying similar triangles, and this can be a bit hard to get your head around, so please bear with me for a bit. So we're going to start with and also the idea that we introduced for the first pair of triangles is actually going to be, it can be equally applied 3 times for all the other sides. So I'm going to do this a bit slowly. Okay, so we're going to start. The idea is that the area of a triangle is equal to base times height. So, and we're going to use this idea to kind of basically say, okay, let's look at these two triangles over here. Sorry, I should have shaded them differently. So let's look at these two triangles over here, which I'm shaded differently. So we're going to look at triangles ACX and triangle ABX. So you can kind of see they're kind of opposite each other. Now, I want to propose that they both have the same area. Because they have the same altitude. And so this can be a bit harder to see, and normally what I would do is that I would rotate the thing, but if you can bear with me for a second while if you can just bear with me while I do it on my iPad, and I'm just going to draw a perpendicular like to the height. That if we just draw the height there to this point, and then you kind of just see, okay, I'm going to draw a parallel line that way that is parallel to BC. Then you can kind of see that the height of both triangles will be the same because it's technically the same altitude. So, and therefore they have the same area. So, and just for those of you who area of triangle is half times base times height. So basically, as long as you've got the same base, as long as you've got the same height, you know that the area of any two triangles will be the same. So the idea behind that is that when we have the same area, what we can do is that we can establish a set of ratios between the base and the area. So what's actually the idea here is that we're going to say, okay, we're going to say bx, and I guess it's so we're going to construct this. So we're going to construct this bx(xc) bit. So we're going to construct this by saying, okay, bx over xc, and then what this is, and what we're effectively also saying is that this is also equal to the ratio of the area of the corresponding triangles. So in the same way we have in similar triangles in which we say a ratio of edges, here we can do the same thing. We've got a ratio of the base is the same as the ratio of the area. So one thing I'm gonna clarify is that when I write ACX in square brackets, that is defined as the area of, sorry, that my iPad's going funny. What's going on? Okay, there we go. So it's defined as the area of triangle ACX. And then so I'm kind of just going to consistently be using this notation because it will just be a bit easier to read in the long run. So bx over xc, so bx over xc, so that is basically going to be the same as the ratio of abx and the ratio of acx. And now the goal of this is not immediately familiar, but what will effectively happen is that we're going to manipulate this in such a way that we've got a different set of triangles, each representative of a different set of areas, which we are then going to combine together. So it's going to be easier for me to do it if say I kind of write it in. Okay, I'm going to try and do the same for the other edges, so you'll have to bear with me for a bit. So I'm going to do AZ and ZB as well. So AZ over ZB in a similar manner, so that's A to Z, Z to B. So, and then I'm looking, sorry, I did not mean to do that. And then I'm effectively looking this way as the height. So AZ to ZB in a similar manner would then be equal to, let's see, so it would be I'm just trying to think about, I'm trying to think about how I want to, how I want to write it. So let's do AZC. No, let's try and do it in alphabetical order. ACZ, and then we're going to try and keep things in. Yeah, we're going to try and keep the letters in alphabetical order. So, and then the other one, which is this one, that's going to be BCZ. Z. And then the third one is going to be CY and YA. So CY over YA is also going to be equal to, so C to Y, Y to A, so the height is going that way. It's going to be, again, in alphabetical order, B, C, Y, and then B, C, Y, and then, we'll do B, A, Y, just to, hold on. No, let's do BAY because it's only changing one letter. It kind of makes it easier for reference. Again, there's no straightforward way of doing it. I thought it'd be easier to do in alphabetical order, but clearly not. So what's going to happen is that what's going to happen now is that what we're going to do is that we're going to try and do things with reference to this center point. I'm going to call that point P just to keep consistent with the notes. So so I'm going to go back to BX. I'm going to go back to BX and XC, and I'm just going to show you that. I'm just going to show you some manipulation first, and then so that's going to be PBX over PCX. CX. So PBX is this little area in here, and that's PCX. And then now we've got a reference point for P. And we can do this in a similar way because once again the ratio to the triangle is similar and the height is the same as well. So PBX over PCX is also equal to ABX, and then that's going to be minus PBX over that's going to be over ACX minus PCX. And then so basically what's happening now is that I'm gonna take this triangle and then I'm gonna subtract this little bit in there as well. And then similarly for the other side. So that will leave us with this triangle in here. Now, the point that it's not clear what the direction is, and we'll eventually come to that soon enough. But this is one of those proofs where it's kind of like you're messing around with a few things, you come up with a few simultaneous equations, then you figure out a way that they all go together. So in the end, what we have here is ABP, and then this one is ACP. So if you can follow like the area subtracting area kind of thing. So similarly for these ones as well, what we end up with is AZ over AB, which is also equal to ACP over ABP. So that's the area ACP and ABP. So you can kind of see that actually the areas are very similar in terms of the denotation. And then for CY over YA, doing similar amount of work, that's going to be equal to BCP, and then that's going to over ABP. So what happens now is that we can actually put them all together. So we'll do that one in black. So we'll do AZ. So the original one was AZB and then AB. So AZ over ZB. Actually no, sorry, I should do that in the same color. So that's AZ over ZB, and then times BX over XC times CY over YA is going to be equal to, and then I'm just going to copy them all over. So ACP, that's over ABP, and then the second one BXC is going to be ABP over ACP. Then the last one is going to be CY over YA, which is going to be BCP and over ABP. Okay, so now we can actually do a bit of crossing out, which is kind of lovely. Let's see if I can do this. I feel like I've copied down something wrong, which I'm going to just ABP over ACP, ACP. So CY over YA is BCP over ABP. AZ over ZB is ACP, BCP. Oh, I made a mistake. Sorry. That's BCP. And then the first one is ABP over ACP. I knew there was something not quite right. Sorry. So what's happening here now is that I'm just trying to figure out how to cancel them all out. But you probably noticed the doubles in now. So you can see the ABP is over here, and then I'm going to use a difficult. So ACP crosses out here, and then BCP crosses out here. And as a result, what that actually happens is that that's going to be equal 1. So it's a bit hard to try and kind of like figure out like effectively the angle of all that, or kind of the overarching ideas, but I guess the overarching idea is that and like say if I had to give a sketch of the previous, it's about manipulating triangle areas, and then because that's what we've done at the start here. And then what we're trying to do is to try and figure out a triangle area with common triangle areas using similar triangles. So this one, like, don't expect to memorize too much of the idea, but I do want, I guess one takeaway idea, which I'll jot down here. So takeaway idea. We want to use similar triangles. Triangle ratios also apply to areas, and then the same fact that two triangles have the same area if the base and the height is the same. So the rough sketch is that basically I can have like an idea I can have a triangle that's with the base like that and a height like this, but I can also have a triangle that's like the base of the same length but a height of the same length, but it can look slightly different, so I could make it like that, and technically they both still have the same area because they have the same length base and the same length height. So those are probably the two main takeaway ideas you want to take away from this proof. So we'll look at the converse of this proof in the next video, and once some of those ideas have sunk in, and hopefully that will be much more straightforward from this one. So until then.